last speaker of this morning session, Susam Boral, also from Indian Institute of Technology in Kharagpur. So when you're ready, please share your screen. So Susan will give a talk about the gravity wave scattering by an array of floating flexible plates having more edge and resting on a Winkler foundation. Yeah, please start. Thank you.
Yeah, thank you. I am Susam from the Department of Ocean Engineering and Naval Architecture of Indian Institute of Technology, Kharagpur in India. Today I'll talk on gravity wave scattering by an array of floating flexible plates having moved edges and resting on an elastic foundation or Winkler foundation. This is a joint work with Shunil and Professor Shahu. The outlines of the talk are as follows. First, I'll mention the motivations and objectives of this study. Then in introduction, I'll emphasize on flexural gravity wave, moved edge, Winkler foundation, wave blocking. Then I'll discuss about the mathematical formulation, followed by the analysis of dispersion relation. Then I'll mention the solution procedures for the scattering problem and some results that will be discussed. And finally, I'll summarize the study followed by the references. Now, motivations behind the studies like this. In the recent decades, the hydrodynamic analysis of very large floating structures is very important due to its wide applications in maritime industries such as floating airports, floating bridges, MOB, and floating cities. Further, these very large floating structures are cost effective and environmental friendly because they don't hamper the marine ecosystem and are easy to construct and can be removed. And also, you know that due to huge population growth and industrial development, the space scarcity is a global issue at the moment. So somehow we need to use the ocean space. Another interesting observation is the motivation is that the study on wave scattering by floating ice sheets and these very large floating structures are analogous because in both the cases, the structure is modeled as a thin elastic plates. Generally, a floating ice sheet on the water can be compressed or stressed naturally due to wind stress and pressure from other sections of the ice, such as continental ice creeping into the ocean. Moreover, the floating structures are often moved with the seabed for station keeping purposes. The objectives of this study are to analyze the scattering behavior of gravity waves by an array of floating flexible plate in the presence of moved edges, to demonstrate the role of moved edge and the Winkler foundation on the behavior of scattering coefficient, to investigate the role of compressive force that leads to the wave blocking, as Oyon has mentioned in the last talk, on the scattering coefficients. Now, what do we mean by flexural gravity waves? When the gravity waves interact with very large floating structures or ice sheets, due to the flexibility of such structures, an wave is propagated below these structures. That is called as flexural gravity waves. It's a coupling of flexural waves with the gravity waves. Here you can see this is the floating bridge, it's the floating airport, and this is a runway on floating ice sheets. Now, in case of mooring, there are different kinds of mooring one may consider, like it's a tension leg mooring, this is a taut leg mooring, this is a catenary mooring, and you can see different conditions of mooring for wind turbines. However, in our study, we basically considered this tension leg mooring. Now, Winkler foundation is kind of elastic foundation, linear elastic foundation that consists of infinitely many closed-spaced linear spring, and the restoring force because of this foundation is proportional to vertical displacements. The Winkler foundation acts essentially like a bed of unconnected springs, you can see here, and that has diverse applications in different areas of engineering, science, including railroad transportation, airport runway, coastal, and ocean engineering. Now I'm coming back to the topic on wave blocking. In this figure, you can see this portion of the water, there is no wave. However, wave is showing in this portion. And it happens due to the occurrence of blocking along this horizon. And this blocking occurs due to the interaction of these gravity waves with opposing uniform current. This figure is taken from this source. And analytically, one can say at the blocking point, the roots of the dispersion relation coalesce. The literatures which are relevant to this study are mentioned here, like Schools et al. In 1987 initiated the role of compressive force on flexural gravity wave propagation. Ren and Wang in 1994 studied the behavior of flexible porous floating breakwater connected by mooring lines. Suzuki et al. In 1996 investigated the dynamic response characteristics of large-scale floating structures resting on an elastic foundation, and they have considered the Winkler foundation. Husking in 2000 developed the dispersion relation in the context of moving load for a floating flexible plate resting on a Winkler foundation. Square in 2011 studied the synergy between the surface gravity wave interaction with VLFS as well as the ice sheets. Kormokar and Source in 2012 investigated the wave scattering by a floating elastic plate which are moved through the seabed. Recently, Das et al. In 2018 introduced the complex physical phenomena that is wave blocking to flexural gravity waves, and this wave blocking occurs due to the vanishing of group velocity. Bormond, myself, Professor Shahu, and Professor Mellon in 2021 explained the scattering of flexural gravity waves due to bottom undulation in the context of wave blocking. And in this year, Pawan Negi with myself and Professor Shahu investigated the wave scattering due to ice heterogeneity under the shallow water approximation in the framework of blocking dynamics. Some basic assumptions that we have considered, like the fluid domain is considered in two-dimensional Cartesian coordinate system. Fluid is inviscid and incompressible. Flow is rotational and simple harmonic in time. The structure is modeled as a thin elastic plate, and for structural analysis, Euler-Bernoulli beam equation with the inclusion of lateral compressive force is considered. Fluid is assumed to be homogeneous, and the water depth is considered to be a finite. This is the schematic diagram. The wave is propagating from left to right. X-axis is along the mean water level. Y-axis is vertically downward. These are the floating plates which are moved with the seabed and resting on the Winkler foundation. And bottom bed is considered as horizontal, rigid, impermeable bottom. H is the water depth. Now, coming back to mathematical formulation, the Laplacian equation in the open water region and plate covered region is the governing equation. In the open water region, the free surface boundary condition is this, and the plate covered boundary condition is obtained like this, where D is the EI by rho G, E is the Young's modulus, I is moment of inertia, Q is the associated with the compressive force term N, gamma is the inertia term, and A is corresponds to the Winkler foundation constant CL. And the rigid bottom bed condition, that is the vertical component of the velocity is 0, and it's given like this. Now, along the plate edges, the interface boundary conditions, that is continuity of velocity and pressures, are these. And the bending moment and shear force in the case of moored edge can be written in this form, where Qj are the smoothing stiffness constant along the edges of the plates. The far field radiation condition is this for a, and here this K10 is associated with the wave mode with open water region. F10 is the vertical eigenfunctions, can be written in this form. R0 and T0 are associated with the reflected and transmitted wave amplitudes. And we have considered the incident wave amplitude as unity. Now, assuming the plane wave solution in open water and plate covered region like this, the velocity potential can be obtained in this form. And this is the dispersion relation in open water region, and this is for the plate covered region. And one can easily obtain the phase and group velocity using the plate covered or open water dispersion relation. Like these phase velocities is defined are defined as omega by k, and these group velocities can be defined as the d omega by dk. Now, this is the, here we have shown the dispersion plots for plate cover dispersion relation, and it's a frequency versus wave number curve. We can see in the absence of compressing force, there is a single propagating wave force for any frequency of the dispersion curve. However, for certain values of compressive force like Q equals to 1.9, the dispersion curve possesses a maxima and a minima. At these points, the wave blocking occurs because of the vanishing of group velocity there. And for any frequency within these two blocking points, the dispersion relation has three real roots or three propagating wave modes for any frequency. And you can see for wave number prior to these blocking points, the group velocity is positive because of the positive slope of the dispersion curve. However, within these two blocking points, the group velocity becomes negative. And beyond it, due to positive slope, the group velocity is again positive. Out of these three routes, any two will coalesce either at the blocking points, and these three routes will coalesce at the saddle point for certain values of frequencies and for certain values of compressive force. This compressive force associated with the saddle point is known as the threshold of blocking. And this point is called saddle point because not only group velocity vanishes, however, the derivative of the group velocity with respect to the wave number also vanishes at this point. Now these are the omega versus k to 0, that is plate cover dispersion curve for different values of elastic foundation constant CL and compressive force Q. As we can see, with the increase in the values of the Winkler constant CL, the frequency of the dispersion curve increases, and consequently the saddle point and blocking point occurs for higher values of frequencies as the values of CL increases. Now coming back to method of solution, and here we have considered initially for a single floating plate. So the velocity potential in the regions, like left part was the open water region, there is a single plate, that plate covered region is considered as region 2, and the right part of the plate region is considered as region 3. Here x less than 0 is the reflected region, 0 to A is considered as the plate length is the plate covered region, and for x greater than A is the transmitted region. This K2 ends are the wave modes associated with the plate cover dispersion relation. K1 ends for n1 to infinity and K2n for n1 to infinity are the purely imaginary roots in the open water and plate cover dispersion relation. And these ans, bns, rns, tns all are unknowns to be determined. Here, these f1n and f2n are the vertical eigenfunctions that are considered in this form. And these vertical eigenfunctions followed this orthogonal mode coupling relation, where for j equals to 1, the relation is this, and for j equals to 2, this is the in plate covered region, it's like this. And this constant cjn's are obtained in this form. Now, using this orthogonal relation with the interface and H conditions, the following system of linear equations are obtained. These infinite sums can be truncated to a finite number of terms, say m, and as a result, we have 4m plus 12 linear system of equations that can be solved that I have solved basically in MATLAB to determine the scattering coefficients like reflection and transmission coefficients. One thing is that here, as the far field is the open water region, so the energy relation here it is followed like kr square plus kt square equals to 1, where kr is the r0 absolute value of r0 and kt is the absolute value of t0, because the incident wave amplitude is considered as unity. And in the case of wave scattering by an array of floating plates, the velocity potentials can be considered in this form, where phi1 is same as in the case of single floating plate. And proceeding in a similar manner as in the case of single floating plate, here we have 4j into m plus 3 unknown coefficients, where j is the number of floating plates. Now, for a single plate, suppose there is a single plate floating in the water, and we have considered the compressive force is prior to the threshold of blocking QCG. Figure this we have varied the compressive force Q. It's this is in the absence of compressive force, and this is in the presence of compressive force, and this is for Fe means free edge, Me means mode edge, and we have in each of the results that without Winkler foundation and with Winkler foundation are demonstrated. W/O means without Winkler foundation, and you can see in the presence of Winkler foundation that higher wave reflection is observed for lower values of frequency, irrespective of the free as well as mode edge. And for higher values, the reflection coefficient pattern is oscillatory with the occurrence of multiple zeros. These zeros are formed because of the occurrence of nodes and antinodes along the reflected edge of the standing waves that is formed below the floating plates. And as the compressive force Q approaches to QCG, a closely occurred optima are observed near the saddle point KCG. And in the case of mooring edge, the wave reflection is more than that of the free edge case. Now, for compressive force within the threshold of blocking and buckling limit QC, basically beyond the QCG, these are the reflection coefficient versus frequency curve. These are the blocking frequencies. Omega SB corresponds to secondary blocking and omega PB corresponds to primary blocking. At the blocking point, the solution of the problem is not known yet, and that's why a removable discontinuity appears there. However, outside the blocking point, beyond the blocking frequencies, due to the presence of single propagating wave, the roots of the characteristics of the reflection coefficient curve is similar to that of earlier case. However, within the blocking frequency, due to the superposition of 3 propagating waves in plate mode, the irregularity and higher number of optima are observed within blocking frequency. And compared to free edge, the more number of optima are observed in the case of mooring edge. Now, in the coming back to the multiple floating plates, and we have considered here the double floating plate and triple floating plate. These results are associated with mooring edge in the presence of Winkler foundation. And you can see this blue line is corresponds to double plates and red line corresponds to triple plates. As the number of plates are increasing, we can see in the case of this red line, a subharmonic peak is observed between 2 harmonic peaks. And also there is a common zero minimum irrespective of the double and triple plate. Thus, a back reflection phenomena is occurring in the presence of multiple plates, and from this double and triple plates, we can conclude that for the n floating plates, one can have n-2 subharmonic peaks between 2 consecutive harmonic peaks. And as the compressive force increases and close to QCG, the reflection coefficient increases. Also, this zero minima occurs for higher values of frequency, and number of maxima minima increases. Now here we have varied the values of Winkler foundation constant, and you can see for higher values of Winkler constant CL in figure B, wave reflection becomes more for lower values of frequency compared to figure A. And now for the compressive force beyond QCG, these are the blocking frequencies. Outside the blocking frequencies, the scattering behavior is similar to that of the single propagating waves, like in the case of Q less than QCG. However, within the blocking frequencies, the optimas and irregularities are observed because of the superposition of multiple propagating waves in plate mode. Moreover, in the case of triple plates, a subharmonic peak is found between 2 consecutive harmonic peaks, irrespective of the frequencies within or outside the blocking limit. This is the surface displacement by considering the compressive force Q greater than QCG. For frequencies within the omega SB and omega PB, the plate deflection becomes irregular, and this happens due to the interactions of these multiple propagating waves in plate mode. However, For frequencies beyond primary blocking point, the plate deflection is regular in nature. Now this is the time domain simulation. Wave is propagating from left to right. Eta 2, eta 4, eta 6 at the plate region. You can see some waves are transmitted back and some waves are reflected here. And this is done for compressive force prior to QCG. So in conclusion, we can mention that the present study deals with the scattering of surface gravity waves by an array of floating flexible plates resting on a Winkler foundation and having free as well as mode edge. A complete solution in terms of the velocity potential is derived using the eigenfunction expansion method to determine the reflection coefficient in the presence of single as well as multiple propagating waves in plate mode. The study depicts that the wave reflection is oscillatory in nature with the occurrence of multiple zero minima. Bragg reflection is observed in the presence of multiple floating plates. This n-2 subharmonic peaks can occur between two consecutive harmonic peaks in the case of n floating plates. At the blocking points, due to the solution is not known, removable discontinuities appear. The study demonstrates a non-uniformity in the plate deflection, just now I have mentioned, for certain frequencies within the blocking limits, irrespective of the number of plates. These are the references which I have mentioned in the literature review. Thank you for your attention.
Yeah.
Any questions?
Thank you, Susam. Thank you. Yep, now it's time for question for Susam from here or any from online. Oh, yeah, Mike, please.
Hey, Susam, thanks. It's Mike Malin here. Thanks a lot for your talk. You're looking well as well. I just had a question.
Hello.
I was surprised by how strong.
Hello.
Hey, Susam. I was surprised how strong the effect of this Winkler foundation was. I felt like in the dispersion equation, it didn't seem like it made a lot of difference to the form of it. Can you show me the dispersion equation?
Hello.
Hi. Susam, can you hear me?
Can you go to the dispersion equation? Susam, can you go to the dispersion equation?
Hello.
Are you disconnected? Can you go to the dispersion equation? Hello.
Can you hear us, Susam? Oh, okay.
Just a minute. Call.
We said, yep, maybe Mike Mellon will send you direct email about the question again. So yeah, that's the end of the morning session. So let's thank our speaker again. Thank you.